just jumped up on the scene, pocket full of green, but the leather and all. I beat that nigga named Jamal, macking hoes in the tight clothes with pretty toes, kicking flows for all the rowdy bros, and it goes look. 1, 2 to the break of 1995. Jamal representing, keep it live. It don't matter how I come on these funk floor tracks with rap. We about to still make snacks. We got bitches for days, riches it pays. Damn shit's changed since back in the day. In my mouth is where the blunt stays placed. Then I get dazed, thinking a phrase to a mate. I'm getting busier, leaving hoes busier than they ever been with the grown men. Busier, straight loony type of niggas that to drop the temperature. Bitch, I ain't really into. So all the tramp gold diggers, keep it real, yo. Gotta keep it real, yo. Keep it real, yo. To all the misrepresentatives, keep it real, yo. Gotta keep it real, yo. Keep it real, yo. Gotta to all the bitch ass niggas, keep it real, yo. Gotta keep it real, yo. Keep it real, yo. Gotta to all the tramp gold diggers, keep it real, yo. Gotta keep it real, yo. Keep it real, yo. I drop the lines of low.
Some nice dreams. See these ice cubes, see these ice creams. Eligible bachelor, $1 million bow. That's whiter than what's spilling down your throat. The phantom, exterior like fish eggs. The interior like suicide wrist red. I can exercise you, this could be your phys ed. Cheat on your man, man, that's how you get a his head. Killer with the B, I know killers in the street. With the steel to make you feel like chinchilla in the heat. So don't try to run up on my head, talking all that raspy shit. Trying to ask me shit. When my niggas figure best, they ain't gon' pass me shit. You should think about it, take a second. Matter of fact, you should take 4B and think before you fuck with little skateboard P.
I'm a gangster, but y'all knew that. The big boss dog, yeah, I had to do that. I keep a blue flag hanging on my backside, but only on the left side. Yeah, that's the crib side. Ain't no other way to play the game the way I play. I cut so much you thought I was a DJ. 2, yippee, 1, 3. SC and double OP, go double G. I can't fake it, just break it. And when I take it, see, I specialize in making all the girls get naked. So bring your friends, all of y'all come inside. We got a world premiere right here.
All right. Let's get started. All right, thanks for everyone who watches this after the recording, or for those of you tuning in live. Just getting started tonight. All right, so what we're going to be covering today is a big topic that's been discussed quite a bit kind of in this industry, especially over the years as we've gotten into this kind of situation where companies are collecting mass amounts of data, and now that we have the technology to actually exploit that data and find valuable insights into how we can grow our business, there's been this proliferation of technology and complex distributed systems and algorithms that are used to solve that problem. So what I want to talk about in today's live stream is understanding the current landscape for big data technology that's used in both large-scale data processing and machine learning, but then implementing something from scratch. So we want to be able to build up a large distributed systems pipeline from the ground up. We want to understand the type of software that we can write to execute across these multi-node platforms. and then package something that can be ran on a daily cadence, for example. So that's what we're going to be looking at today. So let's just dive right into it. So put together a sample architecture that we can talk through just to give context as to what something like this would look like. So what we have here when we get started is we're looking at a big data architecture where we basically have a common story, right? So on the far left-hand side, we're talking about some client that is generating data. This can be pretty much a limitless, unlimited possibilities here, but if you're thinking about modern day web, modern day e-commerce, we're talking about some client that's generating data in real time, constantly, something like clickstream data. So in our example, what we're going to be talking about is what are real-time clickstream events that can be targeted from a website, our synthetic like e-commerce website, and how can we store that data and do processing on it? So imagine that we're storing every single click that a person is doing, and on that click event is a bunch of metadata. So things like the user's IP address, the referrer, where that person came from, like Google ads or Facebook ads. We want to know if they bought something. So we can understand conversion data, like if somebody clicked on something from a Google ad and then that converted to a purchase. So we want to be able to grab and compute valuable insights like this, but we want to be able to do it on terabytes or petabytes of data at scale. And so that's the architecture and why things like this have kind of morphed into this very complicated landscape. So typically we publish this data to some sort of resilient and available system like Kafka. So this is a stream-based technology. You might be familiar with like Amazon Kinesis streams, something like that. So we want, potentially a real-time system that can be used. This is useful both for syncing to a persistence layer like Amazon S3 or a distributed file system like HDFS. But it also opens up the capability to do real-time consumption off the stream directly. What you sync from this stream, a lot of different options. Avro is a very common JSON encoded format, but for our sample case today, we're going to simplify it and just deal with raw CSV data. So that's the kind of very simplified, semi-structured data set that we'll be generating for these tests. And what people do is they take that data as they do this processing and they say, I want to sync that data from my Kafka stream into S3. And this is kind of where the problem begins for these companies is they want to do large-scale data processing and analytics and data science on this massive data lake, right? So there's a data lake, data mart, what have you. It's basically a distributed file system containing terabytes of data. So how do we ask simple questions like, what's the conversion rate of users that, view these sorts of products from Google ads, right? How do we answer those sorts of questions on petabytes of data? And that'll prove to provide valuable insights to the growth of our business, right? So this team that built this pipeline, their job is done, right? But then another team needs to come in, and this is where we start getting into the complex engineering. So there's two avenues that we'll explore tonight, and the first is going to be focused on ad hoc data analytics. So Facebook has built a very highly performant in-memory query execution engine known as Presto. So the reason that Presto is so nice is because it offers this cross-federated ANSI SQL-based query syntax that can federate to a bunch of different sources. So you can have your query cross-federate to Amazon S3. You can have it federate to HDFS, distributed file system, on Hadoop. You can have it hit like Azure Blob Storage, whatever it may be. And the syntax that you're using is corresponding to the ANSI SQL compliant syntax that a lot of people are very familiar with. prior to Presto's release, Facebook had released Apache, which is now owned by Apache, Hive, which used a variant of SQL known as HiveQL, which is still very good. So we're going to kind of compare very quickly the trade-offs here, but when you're using Hive as the query execution engine, it tends to be a lot slower. And the reason it's slower is because its original intentions built in line with Hadoop was writing a lot of data to disk between stages. So when we look at the Presto counterpart, the data that we're manipulating and doing, MapReduce type functionality via our queries are done in memory. So it's a lot more performant. But what we are using from Hive when we're executing through Presto is their metastore. So the Hive metastore is going to be containing partition info for how we're partitioning our data against our data on whatever distributed file system we're using, as well as the location of that data. So Hive metastore could point to, Amazon S3. And so when we send these queries off, Presto will cross-reference the Hive metastore to get that information. But Presto is not a storage layer. It's not a replacement for your standard RDBMS systems like MySQL or Postgres. It is a highly performant in-memory query execution engine. And we'll connect to that and show how that works. Why we would want to use something like this is to do ad hoc analysis. What does our data look like on the fly? How can I potentially prototype a big data pipeline running queries through Presto? How can I validate schemas and so forth? That's a really good job for Presto. Definitely not good for doing large scale, extremely memory intensive reporting operations. That's something Hive is probably better suited to do. So when we look at the bottom half of this architecture, we need to start exploring things like running autonomously large-scale computation, MapReduce filter operations on this data. So when we start to think about the applications that we are developing for this large-scale compute, like on a massive cluster, we want to write code that can do a bunch of filtration. So our input might be 5 terabytes of data, but we want to figure out how to shrink that data. So we might manipulate that data in some way, do transformations. We might filter that data down, and then we might reduce it to understand some holistic output for what we've been computing against. So this idea originally spun out from Google. So Google came out in the semi-early 2000s, and they needed ways to do optimal page rank, right? And so a big part of that was once we, scrape and aggregate the entire internet, we want to be able to look at the contents of the pages that we've collected. And so they wanted a way in parallel to scan all of the links of all of these pages and just extract the link. So that would be one map operation. And then they wanted to reduce. They wanted to understand, okay, how many associations of this link have shown up? Like, what is the total count of this particular link? And that would be the reduce phase. So it followed this architectural pattern of MapReduce, which would execute on, hundreds of thousands of different machines and parallelize those sorts of computations. Now, moving forward several years, Spark came and said, look, I don't want to rely on that sort of architecture because it leverages the disk, which is really slow. And so what we want to do is we want to keep all of that data in memory. And so Spark came along and said, I'm going to support distributed file computation and whatever you want to do in terms of like mapping and reducing your data, but it's going to be kept in memory across these machines. And that has proven to be 10 to 100 times faster than the MapReduce counterpart that Google had created. So what are we doing here when we're talking about like large scale computation? So at the bottom you see we're talking about Python and Scala. These are abstractions that have been built in these languages to communicate to things like a Spark cluster. And so when you type in things like, let me read in my 500 terabyte data set, you just say, load my data. And what Spark will do under the hood is that data will then get distributed and parallelized across all of the nodes that you have in your cluster. And we'll look at spinning up a cluster like that to solve that problem. So when we build these applications, we're doing things like, give me all of the, males that make a salary between this range and this range with an occupation that matches this, right? So you can execute standard SQL statements. They also have builders where you can actually do data manipulation from a more functional approach. We can look at both of those. When we're talking about what do we do after we do these transformations, we might take raw clickstream data from a source like this, and the thing that we sync is potentially like what were the highest selling items for the previous day that were referred by Google search, right? So there are summaries or reports or reduced sets of data that we've computed. And we can output that data, in a variety of different formats. So the ingested source data format might be something like a comma delimited file, whereas the output data might be a highly performant ORC columnar format. So when we're talking about data formats that we want to sync, we have to start asking questions, what are the queries going to be like? If you're only picking, certain elements of your data set, like certain columns, then maybe a highly performant columnar format like ORC or Parquet is going to be good for you. But if you just want to do, schema compliant JSON encoded sync like Avro could also be a good choice for you. If you're reading in the entire row of data, then maybe Avro is a good choice for that since it's a row-based file format. So a lot of different options here, and again, it really depends on your use case for what you're querying. Hey, Romano, thanks for joining. Glad to have you here. All right, so last piece of the architecture that I want to talk about, and then we'll start doing some engineering and implementation here, is Apache Airflow. So, we build up this complex piece of software. We run software against a multi-node cluster to do some sort of transformation. We want this to run on some cadence, right? And that cadence might be every day. It might be twice a day. And there might be some dynamicism baked into the tasks that we have, right? We might need to dynamically calculate partitions where the data exists. We might need to dynamically calculate the output data where we want to store the information, things like that. So that's where Apache Airflow comes into play. And this is a scheduling system that is open source. And Apache Airflow operates on this idea of a directed acyclic graph. So directed acyclic graph, also abbreviated as a DAG, basically looks something like this. So we have a bunch of tasks, and one task might depend on the previous task completing. You can have conditional branching where things start to spin off and do crazy amount of operations. But this is a very common flow. So what do? Well, we authenticate to our cloud service provider like AWS. Maybe we do some partition calculations. We submit a distributed data job against our Spark cluster. We monitor it and upload the results to S3. So these sorts of tasks can run on a scheduled cron job such that these complex things that you're doing every day now become autonomous. And in any case of failures or clusters going down, you can bake in alerting as well, or you can publish telemetry to an external telemetry system like Datadog or New Relic. So we'll be spinning up an Apache Airflow cluster and looking at how that's architected as well. So let's get started. The first thing that we want to do is actually spin up a Spark cluster, and we're going to be using Amazon's EMR service for this. So what you can do is, if you don't have an AWS account, go ahead and log into that. And we want to spin up an EMR cluster. An EMR is the Elastic MapReduce service provided by Amazon. And the cost, you do have to pay for this outside the free tier, but if you select a small number of nodes and you turn on auto termination, the cost shouldn't be more than a couple bucks. So let's get into this. So advanced options. So I'm going to use just the default latest 5.x release of their EMR engine. And we want to install Hive, which we talked about. We also want to install Ganglia, which is a resource allocation monitoring tool, so we can monitor the utilization across our cluster. We'll install Presto, which is, again, the ad hoc query execution engine. We want to install Spark. Zeppelin is a fantastic tool for executing ad hoc jobs in Python against the Spark cluster, so we will install that. And we'll install Livy as well. So Livy is a HTTP-based endpoint for accessing and submitting Spark sessions and jobs to the Spark Big Data cluster. So this is a really fantastic piece of the installation suite that we can use and leverage for submitting our Spark jobs. All right, so I'm going to deploy this in the default VPC. We'll be using the default subnets as well. To keep the costs down, I will be using a smaller master node instance. So all of these can be M4 larges, and the core nodes can also be M4 larges as well. So when we're talking about the master and core nodes, so the master node is what's going to kind of facilitate receiving jobs, potentially receiving requests to load the UIs for the different software that's installed on our cluster. And it delegates to these core nodes. And the core nodes are going to be responsible for storage, running the tasks that are a part of our Spark job and doing parallel computation that we program. So very important for core nodes. In production, you may have a ton of these. You may have very, very large, horizontally scaled core nodes, and you may have n number of instances of these. And this is where the parallelism is achieved. So, if you could have 2,000 parallel core nodes that are operating on petabytes of data, and that can give you a huge speed up. But for us, we're just going to keep it down to 2 in our cluster. All right, and for this, we'll just call it Livestream Big Data Cluster. It's going to be the name of our cluster. Logs will output to an S3 bucket, and if you do not have a key pair, this is what's going to allow you to SSH into the cluster. So I do believe I have one created already. So definitely make sure that you have an SSH key pair pre-created for you. The permissions here, when we're looking at like the EMR role, this role in particular has baked in access to S3. So the EMRFS requests that execute from the EMR cluster will be allowed to pull data from S3. You can change that if you don't want to open up access to your buckets. I'm going to leave it as the default. All right, so once we spin this up, this will take anywhere from 10 to 15 minutes. So while this is booting up, we can start talking about the Airflow cluster. So what's spinning up here is the set of software that's running the Hive Metastore, Presto, Livy, Spark. This is what's booting up now. But what we want is to actually spin up a cluster running Airflow. So Amazon actually does have a managed instance that's new as of 2020, I believe. But what we're going to do is we're going to spin up an EC2 VM, and we're just going to deploy a Docker Compose script inside of it and port forward the ports so we can access it from the open internet. So in order to do that, if we navigate over to the EC2 console, what we can do is we can launch an instance here. And I'm just going to use the default Amazon AMI instance. So if we select that and go around. So we are going to be launching multiple services within the same node. It's going to be a single node Airflow cluster. And as a result, we are going to need a larger instance size. So I'm just going to select the T2 large. It gets me 8 gigs of RAM and 2 vCPUs. And that should be sufficient for this case. Most of this stuff we can leave as default just for the sake of the tutorial. I am going to bump the size of the EBS volume to 15 GB. And this security group will leave as default as well. The SSH will be able to use to SSH into the instance. And the one thing I'll change is the IP address. So this CIDR block right here will target just your network. And if you're connected to a VPN, then it would target the network that your VPN is associated to. All right, so now we can launch this. And I'm just going to choose my existing EC2 key pair here. And we'll just give that a second to boot up. But let me know in the chat if you guys have any questions so far. All right, so we're running now. All right, so it looks like our EC2 is booted up. So what we can do is take the public IP address of our instance. And if we go and hop in our terminal, all we need to do is SSH with our private key and just target EC2 user at the IP address, and we should be good to go. All right, so here we go. You can upgrade if you need to do anything like yum update or anything like that, and this will update everything. Looks like it's already good to go. So again, the first thing that we want to do is we want to run Airflow. So the easiest way I think to do this is to just use Docker. So if we actually navigate to the Apache Airflow Docker images, you will notice that they have a list of their latest here. So this is kind of a self-contained image for the stuff that they run. But the other thing that we want to grab is we want to grab the Docker Airflow Docker Compose YAML file. And the reason I want to grab this is because this contains kind of all of the services that we need. So it will actually set up the Postgres database, the Redis cache, the web server, and so forth, which is really, really nice to have kind of self-contained on in one file. And there's a couple things that we need to modify with this. So if I actually split this and we build a docker compose.yaml file, if we look at some of these variables, the first thing we'll see is the image. So I do not have this environment variable. So what we can do is just hot swap this with their docs. I recommend grabbing a semantically versioned version of this, like 2.2.1. That'll allow you to have a very deterministic version match on what it is you're actually pulling. So I recommend that. So if I paste this here, that'll be the image that we're using as the base. This guy right here, load examples, this Boolean being true specifies that we are loading a core set of sample DAGs that they preload. If you do not want those to load up by default, you can set this to false. But I'm going to leave that as true for now so we can take a look. Pip additional requirements allows you to use the pip installer through Python to download third-party operators for Airflow. Things like connecting to AWS S3, for example, or maybe connecting to Postgres through your Airflow DAGs. That is definitely an option to provide external installations there. The final thing I want to talk about are these volumes. So you'll notice this is actually a local volume mount, and this is the remote volume mount. So you do need to make sure that you have these directories created locally before you actually spin up these servers. And we'll do that remotely. So this looks good for now. What I need to do is get this file over to the remote server. And if we look, this is the default path that we are logged into. So all you need to do is a simple secure copy. So we can do scp-i. We'll grab our identity file, and we want to upload the Docker Compose YAML file. And what we're going to do is we're going to target the user and the IP address. So if we grab the public IP and we put a colon, and this is the path that we want to load it up into. So home/ec2 user, and you'll notice the transfer is complete. So if we check our remote server, we do have Docker Compose here. And if we look at the contents, it's everything that we just edited. So what we need to do here is you'll notice we don't have Docker, we don't have Docker Compose. I've gone ahead and I have pre-made this script here. So this is just a shell script. It'll sudo install Docker. It'll make the Docker Compose binary and executable, and we'll start the Docker daemon. So what we can do is we can actually scp this file as well. So install docker.sh. And once we do that, you'll notice we have the script. So if we just install this guy, we can just go through the prompts. Should just take a minute. All right, so we have a Docker running. If you get an issue like this, like permission denied or something like that, first of all, make sure that the service is started. So sudo service docker start. If you're still getting that, then make sure you are sudo. And you should be able to see the running containers. We don't have anything running right now, which is fine. And now we want to start up the compose file. But remember, when we look at the YAML, remember me saying that the local volumes, DAGs, logs, and plugins needs to exist. So what we can do is we can just make those directories, DAGs, logs, and plugins. And if we simply do a docker compose up, should be able to spin this up. All right, and if you have issues with Docker Compose not being found, could be like if you're not sudo, one thing you can also do is follow the Docker Compose Linux installer instructions. I've had issues with this install a couple times on like CentOS, but these instructions they have on their site are usually pretty good. So we can just install the latest even. Make it an executable. And then symlinking is important, so it goes to your normal path. So Docker compose up. And then again, like any permission denied issues, you may need to be sudo. So things like Postgres, you know, a lot of these images you won't have pre-installed on your machine. So this will go out and reach out to the Docker registry and download all of them. So it should just take a second to get all the images that we need. And one thing that you'll want to check as these logs are booting up, and we'll see this as we start to see like the web server load up, is the logs to make sure nothing died. So if you have a machine, for example, or you're running this Docker compose file locally, then there's a good chance that the memory for your system can't handle it, and some of the containers will just shut off. So it's a big issue for running this locally, and that's why I'm running this remotely. But so far it looks pretty good. If that does happen, just increase the number of gigs allocated for your memory on EC2. Okay, so we're running a bunch of stuff here, but the question is like, how do I know if stuff is working? So first thing we can do is log back into this instance in another session. So I'm going to do EC2 user at the IP address. And if you type in docker ps, you'll notice that we are running a ton of different containers now as opposed to previously. And the key thing is, first of all, looks like everything is just now booting up. And the other thing is we can curl the web server to see if we get any results back. So nothing back yet. So if you do get any issues like nothing comes back, we can go ahead and make sure the ports that we're forwarding look right. So looks like we make this a little bit bigger here. So this right here is the web server. You'll notice that we are port forwarding 8080 to 8080 in the running container. And if you have any errors, you can double check these guys here. So like what you can notice here is that we do have something that exited, which could potentially be an issue. Not seeing any other failure logs that look too concerning. Here's a couple max retries. Again, could be some memory issues. And by the way, like if you are running into memory issues, the easiest way to fix that is to kill your instance. You can go into the instance state and stop the instance. And I believe if you go into instance settings, you can change the instance type. And sometimes for these more expensive containers that you're running, that is a very required thing. So make sure when you go back here, this thing shuts down. These containers right here are going to these VMs are representing the EMR cluster. So if you see a bunch, don't be too concerned. All right, so change the instance type. You can bump this up to like a 2XL if you wanted to. That would give you a little more memory. So now that I've changed that, I'm going to boot this up again. And I'll just start this guy up. Hey, Mo. What's going on, man? The legend himself. Thanks for the kind words. All right, so this guy should only take a couple seconds to boot up. You can refresh to make sure the state looks good. And do know that, you know, these are dynamic IPs. They're not elastic IPs. And so you'll have to change your command. So if I log back in, should have more memory now. What we can do is, again, try and boot this guy up. And you might need to be sudo. And then, of course, like if Docker's not set to run by default, you'll have to do a sudo service docker start. So now you should probably be able to do Docker compose up, and we'll give this a second to try and rectify the failures that we were running into just a second ago. And I usually like to have like another session open just so I can kind of watch the status of some of these services. And this is honestly always the pain, is trying to get all this stuff up and running. One thing also, by the way, if you run into it, these directories, they may not have the permissions required. So what you can do is you can chmod 777 the DAGs logs and plugins directory. And boot this guy back up. So the reason I say that is because you'll see these errors again. You see some permission denied failures. That's on the logs directory. So we want to make sure that the user that we're running inside of the container has access to those core folders. So that's why we need to change the permissions of the local volume mount. That's important. All right, cool. So looking good. Usually if you see the Airflow logo pop up, that's really good news. So again, what I want to do is I want to SSH back into this instance in another session. So you can do SSHI on the identity file. And doing a docker ps, if we curl the local web server, you'll notice that we get back some text, and if we follow the redirect, you'll notice that this is actually a UI. We get a bunch of HTML back in our console. And this is cool, but what's not cool is that if I hit the IP address of this server on 8080, it doesn't load. And I want to be able to view this Airflow in my browser without having to do anything special. And so what you can do for that is you can update the firewall settings. Our security group only allows SSH. So if we modify the inbound rules, we can have HTTP. Actually, we want to do custom TCP on 8080, and we'll just allow our IP address. You can have this specific to like an ENI, like an Elastic Network Interface, or other ranges of different CIDR blocks that you care about. But we're just going to keep this specific to our local network. So now, if you go to the IP address on that port, you'll notice that we have now loaded a non-secure but working Airflow server. And the login is just going to be the Airflow creds, Airflow. And this is what we're looking at. So this is the beautiful Airflow user interface. And each one of these underlined links here is what represents a directed acyclic graph. So you'll see that we have a bunch of tasks, and each of these tasks do some sort of programmatic operation. And you can see that operation inside the code tab. It's just some standard Python code. So if we cross-reference back to this diagram here, this is a directed acyclic graph we would have a bunch of Python functions that do each of these things. The main one that we'll be looking at today is actually submitting custom Spark jobs to the EMR cluster that we spun up. That'll allow us to do like large scale computation and transformation on a remote cluster. And that's what Airflow is going to be really, really useful for our use case. So this is the code for a directed acyclic graph. And again, like you can monitor the status of the tasks here. So we'll definitely be looking at that in great detail. And again, if you are not interested in having a bunch of these preloaded things pop up right when you log in, all you need to do is kill the running containers like so. And when you modify the Docker Compose YAML file, you can set the load examples boolean to false. So now when you Docker Compose back up again, these servers will boot up and you'll have a really fresh, clean slate. So that's going to be the way that we want to do that guy. And by the way, like the developer flow typically is you have potentially like a local Dockerized version of an Airflow cluster. You can build your DAGs locally and run unit tests against them. And then you would deploy them to maybe a staging or non-prod environment. But for us, since it's very memory intensive on my old laptop, we're going to keep it just running remotely on the remote servers. So this guy boots up. When we go into Airflow, as this loads back up, the IP will be the same because all we did was restart the local containers. But the underlying DAGs should disappear once we log back in. So now you'll see we don't have any DAGs, which is good. This gives us a very fresh and clean slate to work with. All right, so as we look at this architecture, what we want to be able to do is we want to simulate like a realistic flow, right? So we want to sync a bunch of synthetic data into a distributed file store like S3. And maybe the first thing we want to do is just query that data. Like how do we look at our data lakes in an ad hoc query execution engine like Presto? So that's what we can do next. So let's go ahead and jump into that. So Makaroo is a really cool website if you haven't used it. But Makaroo is a synthetic data generation tool. So, you know, for us, we're not going to be generating a terabyte of data on my laptop. But what we will do is we'll generate a small data set that we can use for testing. And the underlying infrastructure and code that we write will work the exact same. It'll work the same if it was, you know, 5 kilobytes versus 5 terabytes. That's how we're going to operate. And what we can do is we can discuss like what's the schema that we want to use for the problem that we're solving. So a couple things that they provide is like an ID. So this could be a unique identifier pertaining to a customer, you know, first and last name. This may not make sense in our case. We're just collecting clickstream data. So we're going to kind of create a dummy schema here that's pretty basic. I will do IP address. One thing I'll also include is just a refer information. This will just be text data if they allow me to do that. I just want simple text. Custom list is really good for enumerated values, so we'll use that in just a second. Actually, we'll use that right now. So custom list will be things like Google ads, Facebook ads, could just be like, we'll say organic click, so something that just somebody clicked on. We could do internal, where it's like referred by, you know, a link internal to our website. This would not represent production in any way, but this is a good way to show how we could enumerate different referrers that we support. The reason why we would want to do this is because we can say, you know, X% of our refer data that led to a conversion came from Facebook ads. And so this is where analysts can start to devise really good KPIs or key performance indicators to figure out if it's worth paying for something that we're paying for to help grow our business, right? So that's why I'm including that here. We could have like something like interaction. Interaction could be something like a page load or a purchase, for example. So we may want to know if somebody just went to a page. I'll change that to page view. Or if somebody actually purchased the item in question. Okay, cool. The other thing we'll do is add items. And, you know, in reality, this could be something like a product ID. But in this case, I'm just going to provide a few sample things like, you know, Nike shoes. We'll do pajamas, well, you know, headphones, MacBook Pro, right? We're going to simulate an enumerated set of products that we may sell. And I'll just throw a few more in there, like keyboard, water bottle, you know, random stuff. So imagine we're like Amazon or something. Hey, Chitan, thanks for joining, man. Good to have you here. All right, so I think this is a good schema to start. We're just going to be dealing with very basic CSV data. We'll generate 1,000 rows. And if we look at the raw data, you can see that we have, you know, a bunch of random IP addresses, different refers that are randomly generated, different interaction types, different items that we've sold. So we can actually do like a fairly decent analysis and computation on a small data set like this. So I'm going to go ahead and download this. And we'll use this to query our data. So this is going to be mock data. And what we want to do is we want to be able to query this data. Like, how would I want to know how many, like, what's the number of Nike shoe purchases that I have in this data set? Or how many people viewed Nike shoes? Or what is like the, you know, the number of unique IP addresses that bought something? You know, these are questions that we want to ask in an ad hoc way. And so what we can do is if we look at our EMR cluster, it should be ready now. So if you boot this up, you'll notice that the status is just waiting, I believe. And you can see the master and core nodes are all good to go. And so the first thing we want to do is we want to be able to access the internal like software that we have hosted on this cluster. If I go to any of these right now, the public DNS looks like it's loading without issues. So if we go back and look at something like Livy, this is where the Spark jobs are going to exist. And by the way, like if you do not have access to these UIs, all you need to do is go into the master nodes security groups. So let's take a look at this really quick. So the EMR master node has a set of predefined inbound rules. And if you notice, I have all traffic enabled for my IP address here. So my IP is this. You'll notice if I deleted this and saved the rule set, this loading icon will never resolve. Same for the Livy server. So these will just hang. And if I try and hit any other service that's running here, like Ganglia, for example, you'll notice that it doesn't load. And that's because we don't have a firewall that enables that to load. So all you need to do in that case is modify the inbound rules. The UI dog, what's up, man? Thanks for joining. Inbound rules, we'll just do all traffic, keep it simple, and we'll target only our IP address. So that'll just simplify things. The alternative thing that you can do, by the way, if you're interested, is you can SSH tunnel. So that'll proxy local requests through the master node and load things as if you were SSH'd into the machine itself. there's a little bit more setup required for that, and you use like a third-party extension known as Foxy Proxy, and that allows like the EMR SOX proxy to work. That's another alternative, but we're not going to cover that. But you can look at that in their docs here. Okay, cool. So now if we, pick any of these other services, they should be able to load now, as you can see, just because of that firewall rule. So that's all we need there. All right, so our cluster is up and running though. We're not going to look at this software yet. What we want to do is we want to be able to do ad hoc querying against our distributed file storage system. So what we need to do for that is we can open up like a query client. One that's been really, really good to me is the community edition of dbeaver. So this is a database management system. Also really good for supporting federated queries to a variety of different sources. So it's a good client for those sorts of use cases. What's up, Austin? Thanks for joining. All right. So what we want to do is we want to establish a connection to Presto. So Presto is the in-memory SQL query execution engine, and we want to build a table over our data that we have created. So we've created this mock data. But the question is like, where are we going to query it from? And that's where Amazon S3's distributed file storage system is really useful. So if we come into Amazon S3, we can create a new bucket. And just for the sake of this video, we'll call it like my clickstream sample data tutorial. And if you put underscores like me, this will not work, so you need to replace them with hyphens. And now you have a bucket. So this is a private bucket, but what we're going to do is we're going to upload the sample data that we had just downloaded. So all you need to do in order to do that is drag it from your downloads. So here's the mock data file. We'll go ahead and upload this. Okay, cool. And again, since the EMR cluster has a default role that has access to this bucket, it will by default have the capabilities to read, execute an AWS S3 read operation against this bucket. But what we want to do is we want to connect to Presto, which we did enable on the EMR cluster through our database engine. So dbeaver, you can just add a new connection. And I will be using the Presto SQL driver. Trino, I think, is the newer and more preferred way of doing queries. They have rebranded to Trino, if I'm not mistaken. I do not know if the 5.x release version of EMR supports Trino, but I am just going to start with Presto SQL. And this is where we put the host. So what you can do is actually grab the EMR public DNS name here. And the schema that we want to target is actually going to be, I want to say, port is going to be 8889. And the default database and schema, I want to say, is going to be default Hive. And the username you can just put in Hadoop here. All right, so it looks like we're connected successfully. If you hit finish, we should have a new connection that we can expand. So you'll notice that inside we are using the Hive Metastore. And we have just like this default schema that we're using, and there are no tables because we haven't created anything yet. But what we can do is we can create a table that will allow us to actually query the data in S3. So all you need to do is we can just do a new SQL script. And we want to be able to create like an externally managed table. So all you need to do this is just standard SQL syntax where we create the table. We're targeting hive.default. And then we want to put the table name. So we'll just say like clickstream. Clickstream data is the data that we're going to create. And if you recall, we want to specify the columns that we're supporting. So if we actually look at this data here, we can run ahead on the mock data. And you'll notice that we have ID, IP, refer, interaction, and items. So what I can do is go back into dbeaver, and just to keep this very, very simple, I can do all of these can just be varchars. And this will be the schema that we're using to actually build our table. And remember, this is going to be over the CSV data in Amazon S3. So we're going to create this table, but what we need to do is we need to make sure that we specify where the data is derived from, right? So Presto is not a SQL storage system, it's a query engine. So it needs to know where the data is that it's trying to pull. So all you need to do is specify a with operation and then give it the external location. And that external location is going to be this data that we had just uploaded. And so you can actually give it the entire bucket and it will aggregate all of the underlying data. So if you copy the name of this guy, you can give it an S3 protocol with the name of the bucket and just specify that the format is CSV. And we can see if this works. All right, so Hive CSV storage format only supports varchar unbounded, so we can just remove the upper bound character limit on there. The top 10 elements. What does that look like? So when we run this query, you know, we're using our standard SQL syntax that we're used to, and it actually pulls in a table that looks like so. So really, really cool. You'll notice that it did pull in the first header rows. And I think that Presto has like a skip headers line that you can add. Yeah, so I'm going to ignore that for now, but just make sure that when you are querying this data, you can specify that. And I think you can add like an offset of 1 if I wanted to just ignore that. But for now, here's my clickstream data. And this is really good for ad hoc querying because all we needed to do, like if I only wanted to know the number of page views, for example, we can select star from clickstream where the interaction equals page view. And I actually want to know the count, right? So I can just count the number of rows that match that sort of filter criteria. So if I run this, select count from, we'll delete this. This is spelled wrong, so select count from clickstream. And you also may have to like specify hive.default if you're having issues querying, since we are in the default schema. And you'll see that we have 521. And we could also do the same thing for like purchases. So remember when we created our data, we had basically binary data. We had a page view or a purchase. So if we had 1,000 items, 1,000 minus 521, that would mean that we should have 479 page views, or purchases in this case. So let's run this. So there we are, 479, which matches up because our entire data set without any filter criteria is going to be 1,000, right? So here's, and 1001 is including the header in this case. So again, this is a really great way to fine tune your SQL if you're using Spark SQL, for example, or it's a great way to just do ad hoc analysis. You know, what does my data even look like in this case? And this again is just CSV data that is working and operating just like a standard RDBMS system that you might be used to. And we'll come back to this, but the thing that we covered is kind of this piece here. So here's us doing ad hoc query execution against our distributed S3 data, and we're using Presto to do it, and Hive is the underlying metastore that is storing the metadata associated to these files. So now what do we want to do? Well, what we want to do is we want to build an application that maybe says, you know, for the day that we downloaded this data, how many purchases were made, right? It could be a very simple operation like that. Another question we could ask are, you know, more granular questions like based on, like for example, we wanted to see the number of all interactions independent of one another. So we could select everything here and we could group by the interaction. And this would give us counts for the different types of interactions that we have, right? And so you can see that we have 479 purchases and 529 page views. And we could even come in here and give it the interaction column, right? So it can tell us specific information about the type of interaction and the number of counts that occurred. You can even give aliases to these things where you say number of occurrences. And then let's see here, number of occurrences. Yeah, some of the syntax I'm still getting used to, but there we go. So number of occurrences is now the column, and the interaction is the type of interaction. And these are sorts of summarized views over our data. And there may be a ton of expensive operations that we want to do on a big data cluster like Spark that automates, you know, the execution of these queries. And that's what we'll look at next. So as we're starting to build this pipeline, what we want to do is we want to build from scratch a Python application leveraging the Spark APIs. So what we can do is we can create a new virtual environment in Python. We're going to call this, you know, something like PySpark clickstream. And virtual env is good, and we'll configure this as we go. So let's get started. So as we boot up our new project here, it'll take a second to load. And the first thing we want to make sure that we configure correctly is our interpreter for Python. So if we jump into our preferences, we can go ahead and go into the project and set up the interpreter. You'll notice there is no interpreter, which is fine. We can go ahead and add one. And this right here is the virtual environment we'll use, which is the path that we want to target. And we want to add actually a couple packages. So first package we'll add is the unit test. And actually we'll start with PySpark. I think I'll just use the standard Python unit test library instead of like PyTest. But we will write like a sample unit test just to show how we could test our inputs and outputs before we deploy. Setup tools we'll use to package our code into zip files that we can upload against the cluster. Don't think there's anything else we need, so this should be sufficient for us. We are using Python 3.9, by the way. All right, cool. So this is where we start to do some more advanced development. So first thing we want to do is we want to have some sort of runner, something to kick off our code, and we'll just call it runner runner.py to keep it simple. And we're just going to have a simple preamble here where we say, all right, if we're dealing with the main method here, what we want to do is we want to basically initialize our Spark context, our Spark session we want to have access to, right? And all we need to do for that is we just say Spark equals Spark session. And we'll go ahead and import this. And we want to pre-configure some functionality on this object. So they have a nice builder that we can use. We want to give it like a name, for example. So this could be, you know, clickstream data analyzer. Could be the name of our application. Get rid of this. The next thing that we might want to add is just creating it. So get or create will create an instance of the Spark application. All right, what are we complaining about here? I always forget how many underscores it is. I think it's just 2 though, so should be fine. So next thing we want to do is like, we want to understand in Presto, we're querying data against our data lake, right? Distributed file storage system that might be in HDFS or S3. So the beauty of Spark is that the abstraction for doing that same operation is very, very straightforward. And so the first thing we do is we load that data into an abstraction known as a data frame. Data frames are the newer generation of manipulating data that has kind of surpassed RDDs, or resilient distributed data sets. And they are resilient and distributed underneath their implementation, but they also are more analogous to that of a SQL table. So operating on structured data with named columns. So that's what some of these data frames are going to give you. So what we can do is we can load up this data, and the way that I would like to do that is just saying like, you know, clickstream data, and we just want to read in the data that we're interested in. So in this case, what I'm going to do is I'm going to pass in on a new line the CSV data and the underlying location of that data. Now in production, or in your application, you may parameterize the location of the file that you want to operate on. And we'll do that. We'll walk through like what that looks like. But for us, like, I don't have authorization to S3 right now. I'm not going to set that up. I just want to do a local file. And so the easiest way to do that is I can create a new Python package, and I'm just going to call it source. And underneath source, I will add our file actually. So I'm going to take a small sample of our data, and I'm going to add it in here. Looks like my mouse just died almost. Okay, so new file, we'll call this sample data.csv, and we'll use this. So when we load this data, we'll just simply do source/sample data.csv. Now what this will do is it will load all of this data into this data frame here. And this is where we can start doing operations. And the really cool thing about Spark and PySpark in particular is that you can execute like ANSI SQL statements against your in-memory data sets. And all you need to do that is create like a table abstraction over this data that you load in. So we would literally just do clickstream data dot create or replace temp view, And this is what we would want to name our in-memory table. And I can just name this clickstream, for example. And so when I come in here, I can get my results. So I can do something like, interaction counts. And all I need to do in this case is do spark.sql, and I can literally copy the same exact statement that I had here, right? So we can group by the interaction, and I will literally just copy this and show how similar this is to just standard SQL. The only difference is the table name changes, so this is going to be clickstream. And you just want to make sure that your quotes aren't conflicting. All right, so we can start with this. And if we wanted to view this data, we could just do something like interaction counts.show. And this would get us a good starting point. So what have we done here? We've grabbed the Spark session. We've made a little application that we can play with. And we have the capability of reading in what could be potentially considered as like a large scale set of data from something like Amazon S3. We'll write unit tests around this and parameterize this to make it more production grade. But what we want to do is just create a table over this data and query it so to see if we can query it like S3 or SQL. So what we need to do is first get to a point where we can run this. So this needs to be equals equals. And if I just kick this off right now, we'll see what issues we run into, if any. So first thing we do is Spark gets booted up. Since that's the first line here, we get a Spark session. And by the way, if you're running this locally and you're following along, you'll want to make sure that Spark and Scala is installed locally. If we look at this, you'll notice we just have some syntax issues, which is totally fine. All you need to do, I'm just going to delete the alias for now. We don't need it for this example, but I'm just going to go ahead and run this. We'll also look at getting rid of the header on the CSV file as well, since that can affect our calculations. All right, so let's debug some errors here. All right, so raise exception from none. Part of this is always like schema issues can be very relevant to these sorts of problems. In particular, you'll notice that these are the names of the input columns, and I'm trying to target it by its named value from the header. So this comes into some of the things that you want to do when you're inferring the schema. So if we look actually at their docs, you can Google like Spark CSV infer schema. And it can infer the schema from the header itself. So if you pass an option in here, and we'll do this in PyCharm. This option should hopefully read in if we do have a header. Let me just double check that we do. Yeah, so we have a header on the first row. So this should be able to give us named columns and then keep our SQL the same. So let's go ahead and run that. It'll also get rid of the header too, which is nice. So it doesn't show the headers as like part of your resultant data set. That's pretty important. Okay, cool. So in our small data set, you'll see that we do have the purchases and the page views have been grouped together. And this is the resultant output of our data. So this is really cool, right? And this is just on a small sample of data. But you can imagine, running this over an S3 bucket of 5 terabytes. what it does is it parallelizes this simple expression across potentially thousands of different worker nodes to get you these counts. And that's what we want to simulate. So this ran just locally, right? This is not running on EMR. This isn't running on anything fancy other than a single node, you know, maybe a couple of cores on my machine, but nothing else, right? And so what we want to do is be able to package this and submit this against our Spark cluster. So, you know, as I'm speaking, I'm paying for this cluster and it is waiting for jobs, and we haven't submitted one yet. And so what I want to be able to do is I want to be able to feed it an S3 location or something from some sort of parameterized input. I want it to go fetch that remote data set and run these operations on it and then show me what the results are. So that's what we're going to be looking at next. So let's go ahead and do that. So what we need is we need some automated script to help us package our distribution. We want to have some sort of binary or zip file or egg file that we can upload. And that'll allow for portability when we're running our distributed jobs. So the easiest way to do that is to use something like setup tools. And all you need to do for that is just create a new file. You can call it something like setup.py. And all you need to do, since we have it as part of our virtual environment, is do from setup tools, we'll import setup. And they have a nice API where you pass in the name. So this is just going to be clickstream job. The version of our job is just going to be 1.0. The packages are the things that we want to include. So I'm just going to include the source package. This would matter more if we had like functionality that we wanted to include, like different helper functions, but we haven't done any of that yet. So if there's time, we may add some helper functions and build like a nice little tool set, but for right now, we're just going to package the source folder. And then finally is just the installation packages that we need. So when I say install requires, these are just the third-party packages that I install. So PySpark is the only one that we care about here. All right. So why does this matter? Like, why is this so cool? The reason this is good is because when we come into our terminal, you just do python setup.py install. And what it'll do is it'll run a bunch of commands and generate you a distribution as a .egg file, which is really a zipped distribution that you can submit. And this is really, really useful because when you submit this, all you have is the main class that you want to run, as well as the egg file, which is all the supporting classes. So really cool way of going about this. The other thing that we want to make sure that we change before we submit this is parameterizing the CSV file. So when I deploy this, I don't want to load up my sample file. I want to be able to pull in, you know, a dynamic location. And so for that, you can use Python's like sys.argv. And we can just look at an example of this really quick. So sys.argv is going to be some dynamic input that you can parse. So we'll import the sys library and we'll just grab basically I believe the second index will be the item that we need. So if we go into PyCharm and I import sys, I should be able to come in here and say like, you know, print sys.argv sub1. And this second index from 0, should be the name of the file. So I can replace this. I'm just going to say remote file is going to be the sys.argv1. And this is what we'll pass in. And if we debug this, we'll be able to parse this out and make sure that it's the correct item. The only thing to change is when you're running this in something like PyCharm or your IDE, you want to make sure that you pass this in. So I can just say something like, for local, it would be, you know, source sample data.csv. But when you're running this remotely, when you're submitting it against the cluster, maybe from Airflow, it might be something like S3's path. So something to keep in mind there. So now if I debug this, we should be able to parse this out. So Spark will boot up, might take a second. And if we come in here and we grab sys.argv for the first index here, you'll notice that this is the file path. And so for right now, as it seems, this should work as expected like it was previously, assuming that this path exists. Which it does. But the beauty of this is that we can now pass in any location depending on the environment that we're executing in. So that's what we're going to do next. So what do we have? Well, we want to make sure that we repackage our code now because we've made changes. So just need to go to terminal and do a reinstall. This will give me an updated distribution that we can submit. And now I want to submit this. I want to submit this against my Spark cluster. And if we look at our architecture diagram, we were saying that we have these jobs that are written in Python in our case, and to submit them against the Spark cluster, we can actually use Livy, which is the HTTP-based endpoint that lays over Spark. So instead of doing something like Spark submit, if you're familiar, Livy's like a REST-based endpoint that we can hit, and it'll just ask for a few parameters. So if we look at the Livy REST API documentation, they have a set of parameters that are predefined to basically show you what you would submit to the cluster to start off your job. And a couple of the ones that we care about are things like Py files. So this is the distribution that we just created. I believe that there is like a class name where we specify the main Python file as well. By the way, you can see they do have like a nice little UI built into Amazon. This says succeeded, which is weird because the remote one says dead. But I usually trust the Livy logs a little bit more. And I'm always constantly on this Livy UI because it is a good way to track your jobs that are running concurrently. These session logs, by the way, can usually show you like kind of upfront, does the file that you submitted exist, things like that. So here's the issue for why our thing died. The first one is the parameters that we needed to pass for the remote file didn't exist. And so it's trying to access the S3 location, which we didn't provide. So that's why this is failing. So all we need to do in this case is go to S3. And we want to give it the S3 bucket, just like we did when we created the Presto table. So what we can actually do is grab that, if you remember from this statement here, with the slash, and we want to pass this in as the argument to the program. And if we look at the Livy docs, you will notice that it takes in configurations. There should be args here. So if we go back to Postman, not Postgres, we can give some args. So the args are just going to be another param here. And this arg is just the location. So remember in the code, we expect to take in sys.argv. So this is the argv at this index that we're passing in. So that should be sufficient as the dynamic argument for the location that we feed in. So let's try and submit this and see if we still die. So when we submit a new one, duplicate session name, we can just call this, big data sample stream 2. submits a new job. So when we go check the Spark jobs, you'll see we have a second job booting up. Hey, Lucario. This is setting up a big data pipeline and architecture from scratch. That's what we're working on tonight. So right now we're just submitting some custom Spark jobs against our custom big data cluster that we have running on AWS. But let me know if you have questions. I can definitely answer them. All right, so this thing is still running. We'll give it a sec and see if it completes. So now you can see it's successful. So if we actually look at the session, you can see that here is the big data results. So this is really cool. So what we've done is we've actually ran not on the sample data, not on just this small file here, which was getting us just a couple, output. But this is actually running on the entire data set. And in the same way, we could run this on a data set that was way larger as we please. And so this is actually really awesome. So this is the first output that we've gotten from our Spark job. But now what we want to do is we want to run this from Airflow. So it's been a while since we've looked at this. But what I would like to do is just have a button that I can click that submits this stuff dynamically. So that's what we're going to look at next. So let's hold this thought on the jobs that we're submitting right now and go ahead and take a look at Airflow. So Airflow is really cool because they give you these operators. And so what that means is that when you want to connect to Postgres, for example, you might have a Postgres SQL operator that connects to your DB. In the same way, if you want to submit like an HTTP request, such as this, then you may have an HTTP operator as part of one of your tasks, right? So when we're looking at these tasks, I might have an operator in here that submits an HTTP request to the Livy endpoint. And that's what we want to ultimately construct, right? And so if we look at Airflow, we type in something like Airflow simple HTTP operator. You'll notice this is something they provide out of the box. So they have a sensor to figure out kind of what the response is. That's good for monitoring, like if you get a 200 or a 500, which is cool. But they also have the ability to send endpoints. So one of the things that we want to do is we want to do a post like they're doing here, right? So they're hitting an endpoint called post. This is the name of the task. And this is the data that they're sending, the headers, and this is the response. So this is ultimately what we need to replicate on our Airflow cluster. And what we can do to keep this simple is we can actually steal this. So here's a sample Airflow DAG, and what we're going to do is we're going to try and modify this in real time. Hey Ben, what's up, man? Welcome back to the stream. All right, so what we need to do is just SSH back into our EC2 instance. Because what I want to do is create a DAG that will allow us to submit Spark jobs dynamically to our EMR cluster. So Airflow, not sure if this is the updated IP. It looks like it is. So if we go in our DAGs directory, remember we mounted this volume into our container. So I just need to now create like a Spark submit DAG. So I'll call it Spark submit http.py. And we're going to modify their code. So Apache, they've imported the simple HTTP operator, which is what we're going to use. They also have a sensor. So the first thing that we want to do is we want to change the name of our DAG. So I'm going to change this to like, something simple like Spark submit DAG. Tags can just be like tutorial. I'll leave the rest like so. This docmd is just markdown documentation, which is cool. We will not be using that right now. So I'm going to delete some of this stuff. This we can actually leave as a reference in case we do want to have a sensor, which could be kind of cool. But the rest of this code we're going to delete. All right, so the sample HTTP operator, notice that we are doing a post operation to Livy. Oh, that's right. Yeah, so the way that we actually want to do this, I'm now remembering, is when you look at your connection, HTTP default is what they're hitting. So you can actually override the default connection they're using. I will just use HTTP, the default one. But batches is actually what we want to be hitting. So if we go into Vim, this is going to be Spark Summit. And then underneath endpoint, this is actually going to be the batches endpoint that we're hitting. And the reason it's using HTTP default here, so HTTP default, is because I believe that is the default con ID. But if we look at the simple HTTP operator docs, you'll notice that they give you a parameter for that. Let's see if we can find it. So HTTP operator. Yeah, HTTP con ID. So this one we can actually take if we want, just for better naming convention, and pass this down as a param, and this can be called like Livy connection. So when I say this, save this, what I can do is I can modify the host here for HTTP default. I'm going to edit this guy, and the host will stay the same. No schema, port is good. And now it should be using this connection since we overrode. And that's just Livy connection. So if we check our DAG now, what I can do is clear this, and we should hopefully get a little bit further. So if we check the graph, you'll notice it's running. And it hasn't failed yet, which is good. Normally though, for like a simple post, it should have already finished, so we can double check the logs. So it's trying to send a post, and yeah, so the reason it's probably failing is because EMR is blocking the request, because this request is coming from EC2, remember? And so it's not executing from our IP address, it's executing from the IP address of the EC2 server. And so what we can do is we can actually stop this. So I can shut this DAG off and clear this task. And we just need to make sure that we have a CIDR entry to allow access from our EC2 instance. So if we go to EC2 and I grab the instances, I can grab the IP address of this T2XL. And if we go back to EMR, if we look at the master security group, so over here, there's a security group for the master node. We just need to add an entry to allow the EC2 IP to hit that port. So that is the main issue. So if we edit the inbound rules, We can either be really, really specific and specify the port, or we can allow everything. Since we do own this and it's just for a test, I'm going to allow everything from this CIDR block. So /32 targets a single IP, and this is the public IP of the EC2 instance. I'll do this in production, but I just want to know if one of the... Yeah, so it seems like one of the other security groups were conflicting, which is frustrating. But if we go back to Airflow and we clear this, we should now have access now that everything is wide open. So let's see this queue up. So it looks like it submitted correctly. So now we have, you know, green, which means the job submitted. So if we go to Livy, we should see a new job now. So this one's now starting. So this was submitted from Airflow, which is really cool. So that's all you need to do in order to make sure that you are submitting your jobs against the cluster correctly. But that should do it. I mean, but what we have, so just to recap, like what we have had set up at this point is looking at this architecture. We have a Apache Airflow DAG. We added a submit Spark job task that submits the job over to the Livy endpoint and runs on the Spark execution engine. And we've gotten data, right? And it's pulling that data from a distributed file storage system like S3. It's calculating the results that we want to get back and uploading it into S3. And we didn't do this part here, but what we did do is we did do the ad hoc analysis in Presto. So really great way to query your data interactively and understand like how to get back results. But that should do it. So thank you guys for watching. This has been a long session here, but covers a lot of different data, a lot of different technologies that are used in the big data landscape. So feel free to reach out if you have any questions, but thanks again for watching.